talking about engineering disasters, specifically dam failures, and we'll be doing an investigation of the cause and effects of dam failures, using a case study of the St. Francis Dam failure to exemplify our points. In our group is Jennifer Grenier, Lorcan Muldoon, and Gabby Freitas. The St. Francis Dam was built in 1924 by William Mulholland. It was designed to provide a storage reservoir for the Los Angeles aqueduct system and provide the city with an emergency supply of water for a year. It was more than 200 feet tall, 700 feet long, but only 16 feet wide. Only 4 years later, the dam collapsed. However, this wasn't much of a surprise since from the beginning of construction, shortcuts were taken and many engineering mistakes were made. First of all, the design of the dam was copied from another dam that had been built without any recalculations or taking into account the different topography of the area. And the dam's height was raised 20 feet to fit an extra emergency supply of water without changing the dimensions of the base at all. The dam was also built on bedrock that had been very poorly cleared and was not suited to hold the weight of the dam. Within 2 years of operation, cracks began to form in the dam, but Mulholland thought nothing of them and just had them filled with grout. It was also discovered that he lied and reported the factor of safety to be 4 for the dam, when in reality it was below 1. Despite all of these mistakes and shortcuts taken during the construction of the dam, it is believed that the main cause of failure was the foundation and the ground beneath it. Not only was the dam's foundation not built to sustain the height of the structure and was built on bedrock, but the dam was built on an inactive fault line and where a catastrophic landslide had occurred. This fault line separated the Vasquez conglomerate on the west side and the mica schist on the eastern side. The Vasquez conglomerate is made up of mostly red conglomerate, which is considerably strong, but when it becomes saturated, it can completely disintegrate and turn to sand and clay. The mica schist is a weak and thin layer of rocks poorly cemented together, and when it gets wet, becomes extremely slippery. Mulholland's own team actually deemed the eastern side of the dam highly unstable fractured material that needed to be avoided at all costs in 1911, but completely disregarded that and built on it in 1924. A single study of the dam site or site inspection would have revealed all of these issues. There was never one conducted. There were so many overlooked details that could have completely prevented the collapse of the dam, but the engineers' decision to use the site they did was highly inappropriate for a dam the size of the St. Francis Dam. Mulholland never consulted a single geologist or even a map on the building site. There was no grout curtain beneath the dam, which would have decreased the seepage of water into the materials below. Relief wells and drains were only built under the central part of the dam, which, if they had been built properly, could have significantly reduced the speed at which the water rushed out of the dam when it collapsed, potentially saving hundreds of lives. Additionally, the cracks and faults in the outer surface should have been tested further and taken seriously rather than just filling them with grout, in order to ensure there were no cracks or voids in the subsurface. As can be seen in this picture, there was only a small central piece of the dam that stayed intact after the disaster, and this was the only part of the dam that was built with drainage wells for the water. So if these wells had been built all over the dam as they should have been, the catastrophe could have been reduced significantly or even avoided completely. Within just the first filling to capacity of the dam collapsed at midnight of March 12, 1928, after it had just passed an engineer's safety inspection 12 hours prior to the disaster. There were 12 billion gallons of water stored in the dam that shot out at nearly 20 miles per hour, and the water traveled about 55 miles to the ocean, causing the city to lose power and leaving them in complete darkness while 2-mile-wide waves and pieces of the concrete dam were rushing through the city. The disaster killed nearly 450 innocent people, destroyed thousands of acres of homes, bridges, roads, and farms up to 55 miles away from the site. The St. Francis Dam collapse is believed by many to be one of the worst engineering catastrophes ever. As hundreds of innocent people were swept away from their homes in the middle of the night, it also left the city with $7 million of property damage in addition to the cost of the dam. Mulholland took complete responsibility for the incident, but basically disappeared shortly after the incident. However, it didn't make up for the loss of the city's emergency supply of water or the hundreds of lives lost due to poor judgment from the engineers. As can be seen in this image, the destruction path of the dam spanned about 51.5 miles to the west and 7.5 miles to the east.
As we can see here, we have an image of a graph of the St. Francis Dam. Here is the remaining piece of the dam, this quote-unquote surviving tombstone, and the wing wall. It is from this image that we can see just how many things could have gone wrong that did go wrong. The geometry of the natural setting is in no good form to have a dam on it with the responsibility of holding over 20 billion gallons of water. Not only that, as mentioned before, the conglomerate, which chemically consists of calcite, iron oxide, and silica, saturates upon instant contact. And when it has billions of gallons of water at contact, it will saturate and disintegrate at a rapid rate. Over here, we have the Pelona schist. Again, its composition includes oceanic rocks. It was very easy to crumble as well. The rigidness on the sides of the surviving tombstone explain as to why it collapsed so easily. There was no solid ground. There was no solid rock. It was a disaster just simply waiting to happen. Furthermore, it was assumed that the coefficient of friction was about 0.60. Yes, this comes back out of our physics class. This means that they expected there to be a strong frictional force in terms of the concrete with the rock. However, upon saturation of the conglomerate with its calcite, iron oxide, and silica composition, it disintegrates and there's no friction. So after further investigation years later, it was declared that their assumption was off by over 100% of the actual coefficient of friction. They used 0.60, but scientists later calculated that it should have been within the range of 0.25 to 0.30. What could have happened if we had known the proper coefficient of friction? This disaster could have been avoided completely. This goes to show the engineering ethics side of this problem, where the engineers did not stick with their numbers. There were no numbers taken, and that's a simple response as to why this dam collapsed with such ease, leading to many lives lost and crazy 20-mile-per-hour water bursts across the city. So we now know why our dam failed, the St. Francis Dam, but what are the three common types of failures in general? First of all, environmental. Wear and tear over the years, from oxidation, rain, corrosion, you name it, it happens. That's what happens on our planet. However, in this case, it was the failure to understand the natural setting, the chemical composition of the rock, the fact that it would saturate so quick. It just led to a complete disaster. Secondly, the improper building techniques and design of the dam. You could not use a standard blueprint of the construction of a dam. You simply couldn't. As seen in that image, it's too rigid, the composition's different, but Mulholland and his team went ahead and just used a standard blueprint. This was another ethical mistake. Furthermore, the calculation errors in design with geometry, physics, as stated, with the coefficient of friction being off by so much. And lastly, improper test methods. There was not a review through an unbiased third-person panel. Mulholland just, and fair, he did take the blame, but his decision was very unethical in the engineering world, and many lives could have been saved.
There are three main major impacts of the dam failures. The first one's social, as people are relocated or displaced from their homes after the collapse of a dam. Infrastructure surrounding location of the dam can also be destroyed. In extreme cases, death can result due to a dam's collapse or failure. For example, with the case study that we saw of the St. Francis Dam, around 450 people died as a cause of the dam's collapse. Economically, the impacts are that cities may lose their reservoirs and emergency supply of water. Some dams also provide hydroelectric energy, so the collapse of a hydroelectric dam can also be the collapse of an energy resource. And the effects of a dam's collapse and the spread of the water can cause millions of dollars in property damage. Environmental is one of the biggest impacts of dam failures. Because the collapse of a dam can cause the loss of forests, wetlands, farmlands, and any surrounding areas of the dam. This destruction of nearby land can also cause habitat loss and can lead to the extinction of some species of wildlife in the surrounding areas. This picture right here is an image that displays the effects of dam failures. It's specifically a picture of the St. Francis Dam before and after the collapse. As you can see on the left, that was what the dam looked like before the collapse, and the right shows the aftermath of the collapse and failure of the dam. You can see that the topography and the surrounding landscape of the dam have been completely destroyed because of the rapid flow of water through the habitat, which caused mass amounts of erosion and just all in general destroyed the surrounding landscape around the dam. There's multiple solutions and preventative methods to stop dam failures. The main and most frequent one is routine maintenance checks. These are frequent to ensure the integrity of the structure, and they look for signs of deterioration in a dam. Preventative non-destructive testing methods are another option, and these also maintain the integrity of a structure. They are often tested on prototypes to mimic the effects on a mass scale. Some examples of preventative non-destructive testing methods include visual inspections for cracks and dents, ultrasonic testing, or leak testing. Another type of testing is preventative destructive methods. These are also done on prototypes, but these tests are irreversible and they destroy the integrity of the structure that is being tested. Some examples of these tests include drop testing, pressure testing, and corrosion testing. Forensics testing is another type of testing done to test dam failure, and it is on the internal structure of a unit. They often occur after a disaster has already occurred to help determine the root cause of the incident. The testing occurs using the remainder of the structure or machine that is being tested on. And some examples of forensic testing methods include infrared testing and echo testing. Dam failures actually are relevant to chemical engineering more than you would initially think, as chemical engineering encompasses a wide array of practical applications. As a chemical engineer, you focus on the efficiency of processes, and because of this, you often troubleshoot any problem that could potentially occur in a chemical process. Because of this, many chemical engineers deal with machine malfunctions and unwanted reactions occurring. These accidental reactions are dangerous and can lead to explosions, the compromise of a structure, or just the waste of resources. A major cause of dam failures is deterioration over time, and deterioration can be seen to be the cause of the collapse in our case study of the St. Francis Dam. Many believe that the cause of the collapse was because of the hydroelectric piping of the dam was placed on a tectonic fault line that's bedrock eroded and disintegrated when constantly submerged in so much water. This unintentional erosion is irrelevant to chemical engineering because in process oversight, a chemical engineer has to ensure that each component of a process is running smoothly and efficiently. In the case of the St. Francis Dam, oversight was overlooked, so the dam was not kept up to proper code. So understandably, the dam collapsed and caused mass destruction. As a chemical engineer and as an engineer in general, it is one's ethical duty and responsibility to ensure that any project that you are working on is safe and up to the proper standards. In the case of the St. Francis Dam, the engineers behind the project messed up because they copied the original designs of another dam to construct the St. Francis Dam. The problem in this copying of work is that the St. Francis Dam was in a unique geographical location that had a unique bedrock, unlike the topography of the dam that the engineers copied their designs from. This error in judgment and design due to the topography of the dam's location is the reason that the St. Francis Dam collapsed. The St. Francis Dam failure acts as a reminder of the importance of maintaining high ethical values as an engineer. It reminds engineers not to take shortcuts or the easy way outs of challenging tasks because a simple error in calculation or judgment can result in mass social, economic, and environmental disaster. We've also listed all of our resources that we use throughout our presentation on each slide, but also on this final slide just to see all the resources in one place. And thank you for your time.